I'm Rohit Joshi, engineering lead at Capital One.
I'm Mike Dunn, integration architecture and tokenization secrets platforms for Capital One.
So today I will talk about the journey we took at Capital One, building high performance platforms using NGINX and Lua. So this is in 2013 when I joined Capital One. My first job was to upgrade legacy service bus infrastructure. I was coming from a telco background, and when I looked at the hardware used for that legacy bus for like 32 cores with a hyper-threading enabled 128 gig RAM, and what it was doing was authenticating, authorizing, and routing the request. And I said, hey, I was joking with my leadership, I could run all this infrastructure like 24 domains on Raspberry Pi. And I took up that challenge and realized Raspberry Pi, the CPU is so small. So I was looking for something which is very lightweight, high performant, and I had worked with NGINX in my previous company, telecom domain. So I used that. I used the Lua, which is an OpenResty stack, did a quick prototype which allows to essentially authenticate, does the two-way mutual SSL authentication, authorize based on whether the client has access to particular API, and then route to upstream. And I did a prototype. I showed them that with the HTTP, it was 625 TPS. With HTTPS, given it is not ARM processor, is not optimized for encryption. Throughput was 335, which was still better than one of the domain and traffic we had there. That time, NGINX did not have support for mutual SSL for upstream. So we had the incoming traffic, but outgoing was not there. And at Capital One, our end-to-end traffic is encrypted even within our own nodes. So I had to submit a PR to NGINX, and we started using, and later NGINX had built-in support, which is what we leverage. And when I say NGINX and Lua, essentially we leverage the OpenResty framework. We did modify later for our other platform needs, but that was the start. Once I had this prototype working, I was able to show to leadership saying that look at very low, which is essentially a USB powered device can take this load, and the technology what I choose, why I went for NGINX and Lua. I was coming from C++ background, I had exposure to Java, why I chose NGINX and Lua, and we'll go. So I was looking at what are the web servers, what are the application servers doing, and if you look at, and this is an old image, probably now NGINX would be much higher there, but it was the fastest growing web server. What I liked was the memory footprint, and that's why I was able to run on the BeagleBone or Raspberry Pi. Earlier in the previous company, I had used Apache, which is a MPM multi-process, multi-thread model. So essentially every request you spin up or take the thread from the pool. If you have to support 10,000 requests, you need 10,000 threads. And your CPU is busy just doing a context switching, which is where the NGINX is event driven. You have a one worker, one thread, and you can even assign to CPU core affinity, CPU affinity, and avoid context switching there. So event driven, asynchronous IO, but that was not only enough, because when we take something, any new platform, we know we need to customize. So it has a modular architecture. You can build your own module and load it, and that is where I felt comfortable taking this route, taking into a next level of my prototype, building into a high performance API gateway. That was the first product we built. Now, many of you know NGINX, it has a one master and multiple workers. It also has a cache loader and cache manager. If you are using a static content, it can cache into a disk, bring it into memory, and then also purge if it is expired. The advantage here we have is, if for some reason worker goes down, master is aware, it can bring it up. If it is a single process and if that goes down, now you need another process to monitor and bring that up. So that was easier. The code what you write in a worker is all single threaded. So you don't have to really worry about making sure your code is thread safe, locking and mutex and all those things. So it was much easier development. On the NGINX, why it supports hundreds of thousands of connections. So if you look at, it has a listening port, it listens, once connection comes, it puts into a queue, and with the asynchronous IO, event driven, when message or packet comes on that socket, it now does the read and write. So with the single thread workers, you can support thousands and thousands of connections. The other feature I liked, and particularly very important for the critical infrastructure like API gateway, is zero downtime. Let's say you want to upgrade now, and in the past what we were doing is we bring down and restart, and that's like completely downtime, and then if something goes wrong, then now we roll back, and it was very complex. With this one, you do a reload, your active traffic remains the same on the old worker, your new configuration kicks in and starts supporting the new traffic, and eventually it's all migrated. So that feature was very critical for API gateway to support zero downtime. Is another example when we were looking at what are other application servers or web servers doing. Apache Lite HTTPD, and those are fantastic products. They have like Apache has so many modules, open source modules, but the memory usage and the CPU or number of connections is quite different, and the scalability is key, particularly when you are talking about taking the traffic of company like Capital One, where we are talking about 50,000 requests per second needs to be routed efficiently without adding much latency. So NGINX we all know, and we have heard why Lua, and Mike will talk about it. It was very hard for me to convince, because when I talk about Lua, they said what is Lua, and I said it is a scripting language. It is very high performant, particularly when you use Lua JIT. So and you can embed it. It runs on a small low power device. Also, it runs on a very high-end machines. It was designed in a university in Brazil, and it can be distributed with a very small package. It has support on multiple platforms. So you can see it's multiple operating systems, multiple different type of CPU cores. And the best thing is the binding between C and Lua, and I was surprised that if you load a C dynamic library and if you use a Lua, actually Lua binding is faster than loading a C module and calling a function within a C. So there is a performance out when you call a function from a C library versus if you call a function Lua, that is much more efficient, that binding. And I looked at the binding for Rust and many other languages. This is the best with the least overhead between NGINX and Lua, or C and Lua boundary, compared to C and Java or C and Rust or C and any other language. So, and this is example where there is a library called ZeroMQ, which is a messaging library, and there is not much difference between C++ and Lua binding. So you can see the overhead is very, very minimal there. The next one is Lua versus Lua JIT. So as I mentioned, Lua JIT is much faster, and with the OpenResty, it has built-in support for Lua JIT. You can still use Lua if required, but see the performance difference on some of the functions, the default Lua version versus Lua JIT. So with the NGINX, And Lua JIT code was written mainly in the Lua scripting plus some C modules. We were able to achieve the right throughput with the least amount of latency. Who uses Lua? So this is where I needed all these names to tell my architect groups and leadership that there are people who still use Lua. So World of Warcraft, Adobe, Lego Mindstorm. Even I had to say that it is used at NASA, so it is reliable. Barracuda, Wireshark we know, and there are many a networking tool like Nmap has scripting capabilities. They are using Lua. Red Vision Stack. In fact, in my telco company, we were using Red Vision Stack, and that's where I got the exposure to Lua. They had support for Lua scripting. Redis, RocksDB now have a support for Lua, and at Capital One now we have at least 3 and probably more platform leveraging the NGINX and Lua as a combination to build high performance platforms. I will hand it over to Mike for our architecture journey.
Yeah. So meanwhile, while Rohit was building his prototype, Capital One started to go through our own, I guess, transformation. So back in 2013, we probably would have we did describe ourselves as I think officially it was like a marketing company doing business as a bank. But around the 2013-2014 timeframe, we really realized the criticality of software development and engineering for a financial services company where literally everything that we produce is powered by software. So we started to pivot towards becoming a technology company that does business as a bank. So one of the first things we wanted to do is we wanted to have our customers before the customers be first-class citizens. So the development community, the engineers, were the customers before the real customers. We wanted to start creating software that was easy to consume for each other, so that we could build great applications. So one of the things that was our first program to kick this off was our Dev Exchange platform, which we launched internally first, and then we also launched it externally as well, so that we could integrate with business partners and third parties through API calls. So one of the core sets of features and capabilities that we needed was authentication, authorization, all the usual stuff. You want to have a stable, common place for folks to find things. You want discoverability of your services to be easy and fast for your developers to get to and to onboard. So by 2016, 2 years later, Rohit still had his prototype that he was working on. And we were recovering, I guess, from several technology waves over the last 20 years or so. So we still had the legacy service bus architecture rippling through the company. We still had SOAP and XML appliances. We had for the previous 2 years, we were using a vendor-supplied API gateway. And we wanted to be able to consolidate these down to something that would better meet our needs. So we took a look at the market landscape, refreshed our understanding of all the different vendors that we had out there, evaluated all the open source options that we saw, and then Rohit said, well, take a look at my prototype. And so I was like, okay, but with the performance numbers that you're putting up there and shaming our service bus team with your fleet of Raspberry Pis, that gets a lot of press, but let's see what it can really do. So I wasn't convinced. I hadn't heard of this language called Lua. I'm like, what is this? If it were really so great, why isn't it more popular? Why isn't everybody using it?
It took probably a year to convince them that yes. So then I was like, well, okay, I'm going to build a reference API
in a variety of languages and see if Lua is all that special. So I built an API using Node.js and Express framework, Java and Spring Boot framework, Go and just the Go standard libraries. It really does my heart good to not have to have had requirement for a framework in Go, by the way. I'm a Go fanboy, so apologize for that momentary diversion. And then we had Lua with NGINX. And I was just absolutely amazed at the power of Lua and NGINX together. NGINX has done an amazing job of really transforming what it means to be a web server. And then when they came out with, I guess they may have always had the module support, but allowing people to create their own modules and plug them into an already amazing backbone, lets all kinds of innovation happen, and lets Lua come out there and shine, and all the other things that you can do with it. So at this point, I was convinced, and then we sold it, and then we started to figure out, well, how should we structure this architecture? We've got, and I learned through my prototyping with those services that if you make one wrong instruction call, you can cut your performance in half. So I think I was calling for a timestamp for my log inappropriately, and it cut my performance in half. And so I was like, well, we need to protect our high-speed core and what goes into it, and constantly monitor that so that it doesn't get bloated, so it doesn't slow down. So my boss at the time always quoted me saying, "We don't want to become the bloat that we replace." So we separate out what goes into the core, and we make sure that it's always lean and mean and constantly performance tested. And then we use the rest of the platform is built off to the side in a microservices approach. Developers can build in whatever technology stack they want to. If they want to use Node, they want to use Java, they want to use Go. They can optimize for those concerns outside of what we're building here. We actually use this architecture for all three applications that we'll talk about. So this isn't lessons learned just from DevExchange. This is lessons learned from all the applications we've built on this stack so far. And I'll go into them in a little more detail. So one of the things that's really important to us is resiliency and high speed and very low overhead for all of our internal customers that are very sensitive about what tax we may be putting on their functionality. So we try and avoid ACID transactions and RDBMSs whenever and wherever possible. We also want to be able to run with all of our dependencies down if we need to. So cache what you need locally. If your database goes down, keep running. If your cache goes down, keep running. Whatever your dependencies are, keep running. And so we made sure that we only put things into databases that require ACID transactions. So if we're going to issue a virtual credit card number, obviously we need to be very certain that we're issuing it once and only once. If we're issuing tokens to protect sensitive data, we got to issue that once and only once. And when we coordinate API configuration changes across the fleet of nodes that are out there, we do that in relational databases as well. And there's a whole bunch of things that obviously don't need to go in there. We also want to try and leverage where we can immutability and statelessness. So all the products that we were talking about on that previous slide with the technology waves, most of them use relational databases for all kinds of things, and it was almost always a scalability constraint. So he says, well, we do need to revoke access tokens, we do need to manage those access tokens after they're issued and have all of the functionality around them that we want. How can we do that without requiring a relational database and a lookup on that token? So we decided to create stateless tokens that can be validated without anything running, and we can revoke them. We can manage the full token lifecycle through other means that can be cached permanently. So an example up here is If we want to revoke a token, we just add that token to a blacklist. That's an immutable operation. Once you're added to a blacklist, you can't get off. And since we know the expiration of the token, we can always prune the list so it doesn't become infinitely large. So that's an example of how you can take something where you might be thinking to yourself, I need a relational database to manage this life cycle. Well, if you break it into smaller components, maybe you don't, and you can move on without managing heavy state.
Just one comment here, this JWE. So there was a open source module for JWT, and then we implemented support of JWE on top of that, and then contributed back to that module. So it is available as open source.
And so when you're protecting your RDBMS, we were very lucky in one of our use cases where our workload matches what we needed to do in order to protect it. So we've got a workload where we have 98% reads and 2% writes. So this is protecting sensitive data. The data doesn't shift that much, so we can make lots of read replicas to read data. We can throw caches in front of it so that we can protect that database. We're still looking for higher throughput ACID transaction writes and databases that can give us that. But we do follow different paths to try and protect that database. One thing that's, I guess, an important point on this particular slide, when we were building one of these platforms, which is our sensitive data tokenization platform, some of the consumers of this service need to go through maybe 100 million records a night. And one of the things that we were trying to make sure that we didn't do as that team was starting to try and figure out how to migrate their from a batch lifecycle, which with batch processing windows, to a more real-time process. We didn't want to break their batch processing window. So the challenge I set out for Rohit and his team was, can you make that run in a minute or two? Which meant basically, can you hit 1 million records per second or more? So that we don't really hold up that process and risk bursting their batch windows. So I'll steal your thunder anyway. So Rohit and his team did a great job. They killed it. They exceeded that goal. They hit 2.5 million records per second recently, and so this architecture really can scale. Partitioning. So one of the things that is also critical to that tokenization use case is being able to ensure consistent performance. So if we need to hit that 2.5 million records per second, that we can always hit that 2.5 million records per second, and we can keep that latency very low. So we manually partition our data based on field type that we are protecting, so that we can ensure that that information is always in memory in a cache. We shoot for 100% of our sensitive data in cache for certain data types, so that we can make sure that we can process any load that comes at us and have them not know that we're here. One of the things that was surprising to me when I first started this, so when I was first running those test APIs, I happened to have SOAP UI on my machine at the time, and I was like, man, I did a really crummy job. It only hit 816 TPS on my API, and then somebody told me, oh yeah, well you got to use a real load testing tool. SOAP UI wasn't meant for that. So then, you should use AB. So then I went out and I got AB, and I'm like, oh no, Rohit's scaling so much better than mine. I'm only hitting 7,000 TPS. Then somebody else said, oh, go use JMeter. And so then that hit 24,000 TPS, and that was great and all, but it still wasn't as fast as it needed to be. And then Rohit clued me in on WRK, and none of these load testing tools ever told me that, oh, by the way, this may not actually be the limit of your system. We may be the limit of telling you what the limit of your system is. So that's just something that you need to be aware of if you're building high scalability, high performance things. So we haven't seen anything better than WRK yet. I've been looking at a number of the things that have been written in Go and some other things. So far, WRK is still rock solid for us. So we've taken that up on a single instance node to 240,000 TPS with a single WRK instance generating load on our systems. The other thing I learned out of this is do not run load testing tools from your desktop at work to your AWS instances, because the network police will shut you off immediately. So with that, I will turn it back over to Rohit for the results.
Just a comment on the WRK. So now, as we are building these high performance platforms, and as Mike mentioned, one line of code change could impact your performance. So what we have done is, as part of our automation, we have included WRK as a plugin, and that allows us to run nightly performance tests and understand where we lost the performance between two nightly releases or builds, and then pinpoint particular PR, so we know exactly where to go and fix it. So that is very helpful. So results, as we started from that Raspberry Pi prototype, as we needed more and more features, we built these modules, and some of them are reusable modules. So if you look at, and some of them are supported by NGINX, like load balancing, it's already there. Of course, and particularly that time, the IP refresh was not there unless, so we had to write a layer around that. So every minute we go and resolve DNS value and then update the IP. Authentication, request response transformation, cloud automation, and cloud automation was a key for us because that allowed us to build our second product in a month. We just took the stack as it is, what we built for API gateway, took the automation, modified some business logic for our tokenization, and that was within a month we were able to release in production alpha version of tokenization, because we were able to reuse whole infrastructure around the API gateway. Routing, again, it supports REST and SOAP APIs. OAuth, as I mentioned, we built the JWE, and that's stateless tokens, which allows us to scale unlimited. There is no bottleneck of persisting the token on the database. IP whitelisting, again, is a built-in feature on the NGINX, which we leverage there. Logging, throttling, NGINX has a built-in support for throttling. We also built rate limiting, which works across multiple nodes. I didn't know that now NGINX has that support, but we leverage Redis as a cache, and then use that as a rate limit, particularly the use cases where we have to, like, it's a mandatory and we can't exceed beyond certain number of transactions. We leverage that as a distributed rate limit implementation. Token inactivity, we wanted to have a token expires logic, or given these tokens were stateless, how do we blacklist or revoke? So we had those scriptable policies. At the time of onboarding, we can specify that this API, for if this is the header, route to these servers, or if this is the header, replace with this header. So there were policies at onboarding you can define, and it's executed at a runtime. Monitoring support, TLS, which is again built-in support for NGINX there. Critical piece here we did was we implemented a PKCS binding, Lua binding, which allows us to connect with the hardware security module, HSM, and now we can store encryption keys or other things into HSM and leverage at runtime where needed. And then caching cache is king, that's what I say. What we heard about this performance number, we have multi-layer of cache. So we have a database with the read replicas, then we have multiple shards or clusters of Redis, and then we also leverage NGINX in-memory cache. That is where we get the most throughput. And idea was, even if Redis goes down, if database goes down, as long as our EC2 or our host is running, we should be up and running and routing the traffic. On the our lower side RDS, because our infrastructure is in cloud, Redis, NGINX, and Luajit. And with Dev Exchange Gateway, that was our first product. Second product, as I mentioned, we deployed within a month as alpha, and then now we are able to go 2.5 million tokenization per second. And then we leverage the same reusable modules and built virtual payment cards. You might have heard about in browser, which allows you to check out. If you go to Amazon.com and if you have the in browser plugin, it generates a token rather than putting your credit card number, which means if there is a breach on the vendor side, only we need to do is disable the token. We don't have to reissue your credit card number. It's all secured there. So we built three platforms.
Yeah, the important point to note there is the payment rails as a bank. You have to have extremely low latency services. So it was one of the things that we had confidence in the stack from what we'd seen before it to make sure that when payment processing requests are coming through that we can handle them with no issues.
And our average latency on our payment processing is 1.2 millisecond. So it's extremely efficient. Again, you have to leverage caching, right? Every line of code needs to be reviewed and make sure there is no bottleneck or there is no blocking operation given NGINX is a single threaded. So three products with the prototype what we had started, Dev Exchange Gateway, which now process 2 billion plus requests per day, picking 45,000 per second. And again, these are the observed numbers. The scaling is, I would say, infinite with the number of nodes we can spin up in the cloud. There's no bottleneck.
Yeah. So just to amplify that, I mean, when we stood up Dev Exchange Gateway on just one node to see where we can make one node break, depending on the EC2 instance size, I think we pushed a single node to 160, or actually no, you did it further than that. You did 240,000 TPS on a single node. So Dev Exchange Gateway, there's a lot of extra nodes in there for redundancy, but it's barely running.
Second platform we built is our tokenization platform. We have 4 billion plus records which we have tokenized. Database size is 3 billion terabyte plus, and we have picked 12 billion a day with 2.5 million a second. So when 30 or 40 EMR Spark nodes try to process those large batch files, they run against our 3-node cluster, and still we are able to support with NGINX and Lua and the modules we have built.
And there might be 4 or 5 teams spinning up 30 or 40 node Spark clusters, all hitting our 3-node cluster.
And the third platform, which we again reuse almost all the modules and built, is our virtual cards or virtual payment cards with the least amount of latency between the requests we get. We detokenize, apply the rules, make sure the incoming auth is valid, and then send a response back to our payment processors. Thank you.
Question? Yeah, you ran that test. I wasn't.
Yes.
In that
Particularly on that test, that was an early prototype with which does the mutual SSL of the validating the client, and then once we get the request, we look at the client ID or the CN of the certificate and see if it is authorized for the API endpoint. It's requesting for access. Once that is validated, then we look at what is associated upstream or the backend server, and then we have a way to every minute DNS resolve. We route to that server. So that is essentially a load of.
And were you decrypting and validating the token as well during that test?
So that was a more mutual SSL.
Okay,
we added the
okay.
OAuth support later.
Okay.
But again, with the OAuth as well, it is able to scale. We validate the access token and then check whether they have the right access on the APIs and then route back to the backend server. So I think it is 2 gig, which is the default configuration or the supported with the LuaJIT. That's a good.
So I think NGINX is doing most of our caching for us and not the LuaJIT. I would wager, I haven't looked at it, but I wager our Lua memory usage is very low, and NGINX usage is very high.
So if you look at, we leverage NGINX as a core, incoming requests, outgoing requests, and leverage Lua where some business logic is required. I'll give you an example, like if we have a CN, does it valid from our list of valid CNs, or does this client authorize? So those mappings, again, those mappings are loaded into cache, so it's more a lookup, but most of the heavy work is done by NGINX or C modules there.
Yeah, so those servers have a couple hundred gig of RAM in them, and Lua is not managing a couple hundred gig of RAM.
So this, as Mike mentioned, in our earlier implementation, we had a separate infrastructure for batch and real time. In this one, we combine those. So what we did is we enable the micro batching, which is like on a given request, you can support up to 100 records. And these are all our internal customers who are either migrating data into cloud and they have to tokenize, or our live traffic, or a nightly batch where we work with our vendors, and when they send us the data, first thing we do is tokenize before it gets used within our network. So it's all our internal traffic. One is the legacy data migrating to cloud, plus our day-to-day nightly batches.
And I think we've pushed past time, so thank you very much. Appreciate your attendance. We'll hang out if you have more offline questions.
Thank you.